Okay, let's talk about one last thing concerning dielectrics and dielectrics in capacitors. We're also going to talk about a device known as a supercapacitor, which is a little bit different than our conductor plate capacitor. It's able to store a bit more energy. So why do dielectrics increase our capacity, our capacitance in these capacitors? Well, if you think about a normal atom as having a nucleus which is positive surrounded by electrons, when we place this in a electric field, the electrons begin to stretch and the molecule becomes polarized. So we typically model these polarized molecules as having a positive end and a negative end. And of course they're a little more complicated than that. What are actually forms an hexagonal crystal because of its polarity. In any case, back to our dielectric. So dielectrics in an electric field are actually going to polarize. Now, how does that increase overall capacitance in the capacitor? So when I place my dielectric inside the capacitor, and then I place a voltage across the capacitor, the dielectric will polarize. Positive ends will point toward the negative electrode, the negative ends point toward the positive electrode. As a result, what I actually end up having here is two smaller capacitors, a positive plate here and then the negative ends of these dielectrics here, and a positive and a negative here. So if we think back to our earlier calculation for capacitance and a parallel plate capacitor, instead of having a capacitor with a large distance where the capacitance is going to be lower, we're actually acting like we have two smaller capacitors. With the smaller d, the capacitance is inversely proportional to the distance, and thus the dielectric behaves basically to increase the amount of charge that I can build up on the capacitors. Now, a supercapacitor, this is somewhere between being a capacitor and a battery. In a capacitor, we place a voltage across it, charge builds up, that creates an electric field. We can discharge it very rapidly and use that charge to create current. With a battery, we have an electrochemical reaction that takes place, and this will move charge, but it takes place over a much longer time period than how we can move charge with respect to our capacitor. Our capacitor, basically it's a redistribution for electrons, so it can charge and discharge very rapidly. In a battery, however, chemical reactions have to take place and ions have to migrate. As a result, things happen at a much slower rate. Now, a supercapacitor can generate a much larger storage of charge because instead of using necessarily just the movement of electrons, we use the movement of ions. We can imagine that placing a supercapacitor under a potential difference, that the positive ions are going to move toward the negative end, the negative ions are going to move toward the positive end. And think about it as having the electrolyte, just like a battery, and a semi-permeable membrane in between the two. Okay? Again, for the supercapacitor, just as its name implies, instead of storing, picofarads or microfarads or even millifarads, we're storing farads or even hundreds of farads. This particular supercapacitor operates up to 2.7 volts. That's one of the downsides of the supercapacitors. It can only go to a fairly modest voltage because they're an electrochemical device. So the voltage can't go too high. But look, 500 farads we can store here. So this particular supercapacitor can store 1350 coulombs of charge, where again we're talking about microcoulombs of charge storage on the other capacitors. Okay, so once again, sort of somewhere between being a battery and somewhere between being a capacitor. It can discharge not quite fast as a capacitor, but much faster than a battery. It can store quite a bit of energy, but not to the energy density that we get with a battery. Okay? And again, you can see this when the capacitor is discharged. You have these ions, which are basically dissolved in this electrolyte. We have these polarized solvent molecules. Once we charge it, the ions will migrate, and we get this distribution of charge just like we have in a capacitor. The positive side, the negative side. The polarization takes place. We're storing charge. We're getting positive charges on one electrode and negative charges on the other electrode. Again, what purpose do these serve? Well, for a capacitor, if we need to rapidly charge and discharge charge, we want to use the conventional dielectric capacitor. You do a full discharge oftentimes in milliseconds, maybe even microseconds. But as you can see here, the energy density is really quite low. Okay? Not a lot of energy associated with this, but the power density, the amount of watts, which is joules per second per kilogram, is really quite high. Supercapacitors also have a fairly high power density. Can't quite discharge as quickly, but they can discharge fairly rapidly. Okay? Still not the energy density that we get from conventional batteries or even fuel cells, but if you're using supercapacitors, for instance in regenerative braking, they can work much more effectively than, say, a battery. Now, regenerative braking is the idea that when you step on the brake pedal to slow down, instead of that energy being dissipated as heat through friction, it goes back to the battery to charge it. But the battery can only charge so quickly. So by using a supercapacitor, you can rapidly dump the energy onto the supercapacitor and then use that to either power the motor in an electric car or dump it back to the battery. So, a supercapacitor sort of plays that intermediate role. Again, lithium-ion batteries, a great source of storing energy. It allows us to store electrical energy in the form of chemical energy, but their charge times can be quite long. Here it says 10 minutes to 60 minutes. I have an electric car. It takes hours to charge that thing. They're also limited in the number of times that you can charge them. Sometimes with the lower grade lithium-ion batteries, you can only charge and discharge them about 500 times, depending on how close you go to the maximum charge. Thousands of cycles are possible with certain chemistries, and if you're careful not to overcharge them, but you are limited. Voltage, 3.6 volts, that's what we expect from a battery. Here's the specific energy, 120 to 240 watt hours per kilogram. Specific power, can only get about 1,000 to 3,000 watts out per kilogram of battery. Still, that's not bad, but you got to have fairly large batteries to generate that much power. Cost for a large system can be anywhere from $250 to about $1,000 per kilowatt hour, and usually we expect that they'll last somewhere between 5 and 10 years, depending on, again, the charge cycle. The supercapacitor, we can see charging and discharging happens in a matter of seconds. Life cycle, practically unlimited. If we're talking about 1 million charges and discharges, you're going to have a hard time reaching that. Cell voltage, similar to the lithium-ion battery. Specific energy, certainly you can't store as much energy for the same amount of weight, so we wouldn't want to use a supercapacitor to power an entire electric car. It would just be too heavy compared to the lithium-ion batteries. But again, if you're using it for short bursts of energy, the specific power is quite high. You can get a burst of energy from them, or regeneratively store the braking energy. And cost is still very high. So again, you wouldn't store a tremendous amount of energy in them. Service life is a little bit longer too.